Chapter 12, Deflection of Beams and Shaft. Example number 10, last solution, which is Castigliano's solution. So again, in 1-degree indeterminate structure, beam, which is provided here, we want to know what reaction at A is, what reaction at B is, and what is theta at B. We already solved this problem with a three methods, which is one is integration method and two others is one moment at A is redundant and the other is reaction at B is redundant. Let's see a far simpler approach which is developed by an Italian engineer called a mathematician and physicist which called a Castigliano's theorem and developed by Caro Alberto Castigliano in mid 19th century. Mhm. And he just developed his theory based on determining displacement in a linear elastic system based on partial derivatives from a strain energy function. So let's see how that works. So if it means if we have a beam and which the dominant force on a beam is a deflection and due to a bending. So let's say, for example, in bending, U energy is integration from 0 to L m squared moment squared over 2 EI dx. And if we want to know what is a vertical displacement, for example, at B, xb is a partial derivation of energy over partial of the vertical force. So that's a for a vertical displacement of delta, we'll apply a force of P, then we observe the effect of delta. If we want to calculate theta, we need to apply a moment and observe the theta. So in that case, x of, for example, delta at B is equal to partial derivation of energy over partial derivation of vertical force, which is P, and that's m over ei partial m over partial m over partial p dx. Let's see how that works. So it says in our specific problem to calculate rb, we do know that yb deflection at b is 0 due to our geometry. There is no displacement at b due to ball support there. And if we just want to know what is the solution of the problem for RB based on Castigliano's theorem, if we just make a cross section at the length of x from the right. So that says x from the right gives us mx, and that's a wx, converting the distributed to concentrated load. And definitely we have a reaction at ball support at B. So if we develop the moment equation about x and consider counterclockwise as a positive direction, that says it goes to 0, mx including mx equal goes to 0. It just says a negative mx because that's a counterclockwise uh, moment, a minus, that's again a counterclockwise, sorry, that's a clockwise and again a clockwise, so that goes by both negative wx, a half of wx squared, plus rb, which is a counterclockwise, which goes by positive rb times x equal to 0. That's a moment equation. If you develop that, that's rx times rb times x, a negative minus a half of wx squared. And as soon as we have a moment equation, Castigliano's theorem, it just says a partial derivation of u over partial of rb. Mhm. So, and you can easily see partial m over, because our u is due to m, and that's a common in beams because the energy function is based on moment. So that's partial m over partial of RB reaction at B. And if you make a partial derivation of RB, that just gives you that's X. And if you just replace in the formula, it just says YB, which we already know from the geometry that is equal to 0. That's 1 over EI, 1 over EI, integration from 0 to L, replacing the M, that's M. We just replace that based on M equation. And then partial M over partial P, which is RB here, and that's a X. We replace that here. Mhm. And if you do, and we do know that it's equal to 0. And if you do the math, it just gives you 1 over EA RB times L cubed over 3 minus WL to the force over 8, and that gives you a RB is equal to 3 over 8 WL, which we already calculated with all the previous methods, and it's a uh, just with a maybe 2 or 4 lines, just one page. It gives you, we didn't have any moment drawing and a moment area calculation or integration based on a conventional approach. We do have integration, but it's a simple integration with a Castigliano's method. And if you, as soon as you know what RB is, RA is 5 over 8 WL. And for calculation of theta B, you just need to go for appropriate force. So that's a moment. So for calculation of theta B with Castigliano's method, this time we say theta, it's a partial derivation of u over partial m at B. So this time we apply a moment at B. Uh-huh. And we observe the theta. Again, we cut the beam through from a distance of x from right and develop the moment equation. And if you do so, it just gives you a minus mx, a clockwise mx like previous part, minus 1 over 2wx2, this time a negative mb. We do have also a negative mb, which we just uh, developed here, plus a rb times 3 3 3 over 8 WL, which is the, that should goes by, I think that goes by WL squared. Mhm. No, WLX. Yes, that's a RB times the distance, which is X. And if you develop the M equation, it just gives you this equation. And because at the beginning we didn't have any moment at the original beam, we don't have any MB, so we just put MB in the moment equation, it goes to 0. Mhm. So again, if we have moment equation, just a partial derivation of M over a partial MB goes by 1 for partial part, and then for the numeric value of M, because there was no M at B, it just goes 0. Mhm. So we first get our partial derivation, then replace with the real value for that. So, and if you do so, it just gives you a theta at B is equal to 1 over EI, and that says, I think that's a WL times X, WL times X. Yes, WL times a negative 1 dx. And if you do the integration, it just gives you, yep, that's correct. There was a WLX, and it just shows up in this part. Theta B is a 1 over 6 WL cubed, a positive one, and a minus a 3 over 16 WL cubed. If you calculate it, that it gives you a negative 1 over 48 EIWL cubed, which is exactly the amount of theta b which we already calculated with different methods. So that's a comprehensive example with a 4 solution, which is the first one integration, the last one Castigliano, and 2 in the middle, just a considering a redundant reaction, either a moment at a cantilever fixed part or a reaction at at the end of the beam, which is RB. Thank you.